Welcome back to the lessons for electrochemical cells. Now, electrochemical cells are everywhere in daily life. From the battery in your cell phone, laptop or tablet, to the newer cars on our roads. They even make most of the really important chemicals in our homes. Most of the periodic table does not exist as elements in their natural form. They often lose electrons like metals or gain them like non-metals. So, in order to control this behavior and make use of the substances, we need to use redox chemistry. The redox we have learned so far has to do with chemicals reacting in a single place or container. But it is possible to separate the chemicals into different containers called half cells. But before we get too carried away, let's look at a simple example of electrochemistry. Electrochemistry is mostly about redox reactions that happen in aqueous solutions. That means that the substances are dissolved into ions in most cases, especially substances we call salts. When ionic substances dissolve, remember that they dissociate into cations and anions. In electrochemistry, we treat them as separate substances called species. The sulfate ions, the copper 2+ ions, and even the water are considered species. So, let's take some copper sulfate and stir some into water. The crystals of the CuSO4 split into copper cations and sulfate anions. These ions can now be involved in redox reactions. Also remember that the substance that is in the beaker in the largest amount is actually the water itself. Water can also be a redox reactant, so keep that in mind. Some zinc metal is now put into the beaker and something strange starts to happen. The blue color of the solution is disappearing and the zinc is now covered in a brownish red powder. How do we explain this? Using reduction and oxidation reactions, of course. Let's look at the table of standard electrode potential. Step 1 is to find all the species we are given. Be careful to look to see if the species are hiding in more than one place. Circle them with a pencil. Step 2 is to find the strongest reactant. We can see that the arrow on the left points down, so we choose the Cu2+ as it is the furthest down and the strongest oxidizing agent. All the substances on the left are oxidizing agents because they cause oxidation in other chemicals. Now, the choice on the right is easy. The zinc metal is the strongest reducing agent. Step 3 is to write out the reactions, starting with the substances we choose as the strongest. That means we can say copper 2+ plus 2 electrons goes to form copper metal. Make sure to write it as a single arrow in the middle. The zinc metal is read like this. Zinc goes to zinc 2+ plus 2 electrons. Step 4 is to balance the electrons and combine the reactions into a net ionic reaction. Luckily, this reaction already has 2 electrons on each side, and this means that we can cancel the electrons and add each side together. When adding them together, we can see why the blue color went away. The blue copper 2 plus ions become solid copper metal, making the brown powder on the zinc surface. The two half reactions happened in the same container with electrons moving from the zinc to the copper 2 plus ions. They did this spontaneously, and this makes sense looking at the redox table. A line joining the oxidizing agent to the reducing agent makes a positive slope, but that means that the electrons have energy when they move, and we can make them do work. That is how cells or batteries work. A galvanic cell is made by separating the two half reactions into half cells. We usually have both the oxidized and reduced form of the same substance in each cell: zinc and its cation, and copper and its cation. They are connected by a wire to let electrons move and by a salt bridge to let ions move. We usually draw these cells so that the cell where oxidation takes place is on the left. That's the zinc in this example. The reducing happening on the copper electrode is reduction on the right. Looking more closely at the wire, we can see that electrons leave the zinc metal, go up the zinc rod and through the wire. On the way, we can measure the energy of the electrons or even make them do work, like switch on a light. After they've gone through the wire, they travel down the copper rod and meet the copper 2 plus ion and combine to form copper metal. Something really strange happens during this process. The zinc turns into soluble ions, which then move into the cell. The copper ions turning into copper metal make the electrode grow. In fact, this is the way to purify copper metal, but that's a topic for another lesson. The salt bridge is really important because the zinc electrode is making an excess of positive zinc ions. That's because there are now more positive ions than negative ions. So, two things start to happen. The positive ions start to move into the salt bridge towards the copper side. The negative nitrate ions move into the salt bridge on the copper side to meet and keep everything neutral. Notice how the cations are moving towards the reduction reaction. We call that side of the cell cathode because of it. Cations moving towards the cathode. The anode, well, that's where the anions are moving towards. Cool, huh? Now, you're probably wondering what all those numbers on the side of the redox table are. Those are called reduction potentials, and we'll talk about them in more detail in the next lesson.